Hi everybody on YouTube, can you hear us? You can just type it in the chat. We'll get started in just a bit.
He's been in the library for so long.
That might work a little better.
It's soft.
Here,
It's got
yeah.
a soft light bulb.
Oh, now we can't see.
So I plug it in. Has your retinal scan. Oh, thanks. Oh, that's the It's a soft white.
Oh!
Nice. And where does this go? What is this?
That is Darian's. Darian's let us borrow it.
Oh, there we go.
Yeah.
Big win.
Okay.
Perfect.
We'll get started. All right. Hi, everybody. Welcome to the first lecture of the semester. We're very excited to have our own T.Craig Sinclair to give the lecture. Also, I am super excited with the amount of people we have today, so clearly college hour works. I think this is the most people we've seen in a while. So I think we have an incredibly exciting lecture series coming up. Our next lecture is going to be on March 20th with Aaron Besler, co-founder of Besler & Sons and assistant professor of architecture at Princeton. On March 27th, we'll have Kasim Shepard, co-founder of Urban Omnibus, founder of SQ Projects, and currently an associate adjunct professor at City College. On April 10th, we have our own Vanessa Alicea Chukwi, who's going to be giving a lecture about her fellowship research. And then our last lecture of the semester is sponsored by AIA New Jersey, and it's Susan T. Rodriguez, and that will actually be taking place at Kane Hall at 5 p.m. So that's the only one that's not during college hour, but there's food, so you should definitely go. All right, so let's get started. So for some of you, you already know T.Craig Sinclair. For those that don't, T.Craig Sinclair is a New York-based architect who conducts experiments on space, technology, and perception. Trained as an architect, Sinclair has previously completed research on the deep ocean during a 2021-2022 Fulbright in Norway, and trained professionally as an architect under artist Olafur Eliasson in Berlin. His art and design work is award-winning and has been shown in galleries around the world. Sinclair's writings have been featured in publications like Clog Journal and Arcade. He's currently a faculty here, and at the Norwegian University of Science and Technology. He received his Master's of Architecture from Pratt in 2016 and studied philosophy as an undergraduate at Linfield College in Oregon. So with that, welcome, T.Craig.
Thank you, Stephanie, and thank you everyone for being here. I just really hope everyone here at Kane understands the amount of work that Stephanie puts into this lecture series and to get everything ready. It's really quite an effort, and I hope everyone appreciates it. I'm really happy to have this opportunity to share my research with the wider Kane University community. But before I started, there are a few organizations that facilitated this project over the last years that I need to thank. First, the US-Norway Fulbright Foundation, especially RENE 11, the Norwegian University of Science and Technology, and the Kunstakademiet i Trondheim for hosting my research. Special thanks there to Florian Schneider, Nabil Ahmed, Mari Bastashevsky, Jakob Jessen, and Maria Gonzalez. To Olafur Eliasson, Vanya Zunko, Jeffrey Garrison, and the rest of my friends who are part of the SOE team. A special thank you to J.M. Letgart for his support, conversation, and shared love of Scottish rugby and single malt. To my family tuned into the stream, my mother Elizabeth, father Tom, and Brian, Emily, and Louis Reed. And most importantly, to my fiancée Lauren, who turns out went to high school with Stephanie. Sort of a strange detail. A little bizarre. Whose collaboration, intellectual sounding board, and frankly, emotional sound booth have allowed this project to flourish. Without these people, this research and project would have never happened, and I'm greatly indebted to all. Before I start, I do want to emphasize that I do other work, but today I'm going to be concentrating on my project on the deep ocean that I've been working on for the past couple of years, and will continue moving on with for the future. This is actually the first time I've shared it publicly in this type of arena, so this is really exciting to be doing it in front of a home crowd, if you will, and I'm just really, really happy to be able to talk to you today. But without any further ado, I got this mouse isn't quite cooperating. Chapter 1. In 2013, the UK's Ugly Animal Preservation Society elected the blobfish as the world's ugliest animal. One look and it's pretty clear why. The blobfish's greasy skin, soft body, and droopy facial expression kind of fluctuate somewhere between mildly gross and cuteness overload. It looks back at us with a visage that seems perpetually stuck in a case of the Mondays. It is no surprise, then, that the blobfish has become ingrained in culture, whether as a cartoon, a plush toy, or even a Halloween costume for young kids. Despite the memes, however, in its natural habitat, the blobfish actually looks like this. Cycrolutes marcitus inhabits waters primarily off the coast of New Zealand at approximately 1,000 meters of depth below the surface. At this depth, the pressure of the water column exceeds 100 times the pressure of the atmosphere. To survive at this sort of pressure, Cycrolutes marcitus's body is primarily made of gelatin. So if it usually looks like this, why do we know it like this? Well, when caught in a trawler's net and brought from its natural habitat to the surface, Cycrolutes marcitus undergoes an extreme transformation as it ascends the water column, most similar roughly to the bends. It experiences pressures for the first time 100 times less than its native environment. In the few-minute journey to the surface, the blobfish's blood boils due to the differential pressure, and its gelatinous body inverts, resulting in the blobby, deformed, fun face we have come to know. The blobfish is a meme because of a process of slow torture that it experiences in the process from its native habitat to the surface. As humans, we often think that our experience of space is normal or the neutral. Yet all organisms have evolved to inhabit their own ecosystem. Humans cannot visit the deep ocean without bringing our own atmosphere with us, just as Cycrolutes marcitus cannot survive the surface alone. In 2018, while working as a designer at Studio Olafur Eliasson, I was tasked with a long-term research project on the space of the deep ocean. The goal was incorporating it into what Olafur likes to refer to as our sense of planetary we, the sense of solidarity. After the project died, unfortunately, but I adopted it and made the project my own by orienting it specifically as a study of architecture. Consisting of depths more than 1,000 meters below the surface of the ocean, the bathypelagic zone and below, the deep ocean is where soft systems and deep time converge to form a space that is dark, groundless, slow, and sparsely populated. Where the surface is bound by gravity, the physics of the deep ocean are a balance between buoyancy, suspension, and pressure. For humans to visit, vessels must seal in humans' atmospheric conditions from the surface into what Peter Sloterdijk describes as an absolute island of human habitability immersed in certain depth. The gases inside the human body are not able to withstand the water pressure at this depth. But even if it could, there's no light to see, no hard surface to touch, no air to smell, and no ground to walk. The deep ocean deprives humans of our body's tools to comprehend and navigate a visual scene. No sunlight penetrates below 1,000 meters, even though the deep ocean contains the majority of Earth's habitable biome by volume. While many organisms deploy bioluminescence, it's not meant as a headlight or an attractor like you may have seen in the movies or from a bad high school biology professor or teacher, but rather to confuse predators by mimicking light higher in the water column. The slowed activity of life amongst deep ocean dwellers results in longer lifespans and slower bodily rhythms. For instance, bacterial lifespans that are but mere hours on the surface can be 1,000 to 3,000 years in the deep ocean. Larger life forms in the deep sea can live for centuries. Everything here moves slowly. Currents, lifespans, metabolic rates, movements, energy expenditures. Most organisms that live in the deep ocean float freely, obtaining energy by filtering marine snow, which you can see in this image, which is biologic detritus from higher in the water column that falls down. Essentially, it's fish poop and dead diatoms. Food here is found, not hunted. However, this perceived void is anything but. Despite its dearth of sensory inputs that humans can use, the deep ocean is alive, estimated to contain 10 to 30 million species. Most handle the intense differential pressure with bodies that are largely gelatinous. These creatures float seemingly aimless through the ocean volume. Sometimes organisms are difficult to separate from the ocean water itself. To navigate in the dark, organisms here primarily feel their world by receiving environmental cues imperceivable to humans. Most senses are derived from cilia and neuromass that create a spatial model of the world by feeling vibrations and perturbations in the water column. Humans do not hold the same sensory apparatus. Deep ocean organisms may go through life without light, but they don't need it to sense their world, as their senses are finely tuned to the bands of sensory stimuli that are offered by their environment. Without any of our species' ability to make sense of and feel space, I, as an architect, initially began this project seeking to understand how space functions in the deep ocean. What does it mean for architecture to be in the deep ocean? What could our discipline learn from such a foreign but nearby environment? In general, how is space constructed in the deep ocean? Chapter 2. On June 6, 1930, quartz windows were bolted into the steel shell of the bathysphere, and naturalist William Beebe and engineer Otis Barton squeezed into its 4-foot interior diameter for a 2-hour voyage to become the first living humans to submerge themselves beyond the reach of daylight. Beebe reflected on their view in this vessel, a precarious state between worlds. And I quote, "To the ever-recurring question, how did it feel? I can only quote the words of Herbert Spencer. I felt like an infinitesimal atom floating in illimitable space. When confronted with this world within our world, still cosmically more domestic than foreign, Beebe and Barton were without the sensory tools not only to describe the space they observed, but even spatially comprehend it. What they could see out of the bathysphere's windows was without horizon, without ground, without perspective, without any of the objects our sense of vision uses to construct a visual scene. While Beebe made several significant observations of deep ocean fish, the technology of the human body, supported by the architecture of the bathysphere, was fundamentally ill-equipped to form any cognitive model of the world, from the spatial inputs provided by the deep ocean. The potential sensory stimuli of the deep ocean constituted a sort of spatial nonsense to the explorers, a sensory static outside human sensory motor comprehension. Nearly 90 years later, humanity has learned little more than Beebe and Barton. Where the topography of Venus, for instance, has been mapped to a resolution of 1 point of elevation every 100 meters, the deep ocean seafloor as a whole has only been mapped to 1 point of elevation every 1.5 kilometers. The entire scientific understanding of the midwater deep ocean comes from either direct observation by humans or, more commonly, with remotely operated underwater vehicles, ROVs or rovers, that transmit optical, sonar, and other data to researchers and technicians on the surface. Only a few sparse cores of the deep ocean have received direct observation, yet new species are discovered on each expedition. Scientists studying the deep ocean, along with the mineral extraction industry, already hold artificial tools for sensing, measuring, and navigating the space. Confronted with spatial conditions that defy our species' basic comprehension, the robots we send in our stead construct representations of the environment that can be processed and understood by biologists, environmental scientists, and other researchers, which I found interesting as an architect. To understand the spatial models produced in this seemingly inhuman environment, I spent the last year embedded as an architect within the ocean research community at the Norwegian University of Science and Technology in Trondheim, Norway, which is a leader in ocean technology research, and also in contact with several other European research institutions. There we go. There, utilizing a research methodology that took inspiration from Bruno Latour's ethnographic study of laboratories, I conducted interviews, held conversations, observed field research, and visited labs to analyze the models, images, and diagrams produced by robots that researchers send to the deep ocean. My visits included groups like the Trondheim Biologic Station, NTNU Ålesund, Sintef, the Slettvika NTNU Field Station, and other private companies around Trøndelag. Each discussion and visit was documented as a qualitative data point in a conversation log, and accompanied by photos and video, which was eventually shown during my solo show, Deep Ocean Architectures for Other Than Humans, which was shown at NTNU this past June. Each log entry was collaged together with research images, ideas for my literature review, and other artifacts from the research process in this wall-sized work called The Deep Ocean Wall. This acts as a sort of non-linear atmospheric display of my collected research, for which each individual visitor could navigate at their own pace, and where each observer could leave with a different narrative. Through this research process, operating in an other-than-human world, I expected to find an architectural experiential language that could provide new means and methods of articulating and feeling space for humans. ROV builds tend to resemble a smaller-scale version of Cedric Price and Joan Littlewood's Fun Palace. Open grids of superstructure within which infrastructure and equipment can be inserted and interchanged. Depending on the instruments loaded, rovers can collect water samples, make measurements, and carry materials back to the surface with robotic arms. Sometimes these assemblies are entirely haphazard. A year's worth of research for one PhD at the Max Planck Institute for Micromarine Biology was reliant on the mechanical integrity of rubber bands deployed at 2 kilometers of depth. It's incredible. Actually, it was on this apparatus as well. Other ROVs, like those run by the oil industry, better funded American institutes like Woods Hole or Mbari, and the research completed at NTNU are sleek-looking robots with carbon fiber skins, linked to the surface through electronic wires and communication cables. Engineers in these institutions handle budget, which is the most substantial constraint in ROV design, by either designing robots to be multifunctional, holding the capacity to run several tests in one drop at a single location, like this one you're seeing here, or by designing robot bodies to be small and mobile, sometimes resembling torpedoes like these, capable of running single experiments over a broad area. Some ROVs go cordless by pre-programming routes, but the sort of autonomous and swarm technologies touted by press releases are many years and, more importantly, several million to $1 billion away from any kind of realistic application in the ocean at all, much less the deep ocean. Prototypes and renderings are more likely to be used in fundraising and institutional marketing than in any kind of imminent use. As an aside, the potential benefit of autonomous ocean research isn't just the cool technology. It's actually that the most expensive part of any ocean research expedition is bringing the researchers along to do the research. If researchers could somehow stay at home and just pre-program an ROV to just go and do it several hundred miles away, millions and millions of dollars could be saved and all sorts of new research could happen. Of all the methods for deep ocean data collection, the camera is by far the most popular. Sort of modern day equivalent of looking through B.B. and Barton's windows just from the safety of a remote screen. ROV mounted cameras operate like eyes on a stick, extending the human sense of vision to places the human body could not otherwise visit, either physically or financially. The camera alone, however, can transmit little to scientists in an environment without light, obviously, so artificial sources have to be brought with it and be projected into the abyss to find objects to bounce light off of. Even so, Mbari's social media and live streams are filled with perfect shots of extraterrestrial-looking ocean creatures, floating unorientable and groundless. And it's always accompanied by excited scientists describing their biology from an above-water sound studio. Look, I mean, this footage is compelling. It clearly is. But it's just as limited as BB was in a steel sphere to the complexity of the environment. No matter how advanced, cameras only capture a brief glimpse of objects in the deep ocean and suffer, frankly, from Whitehead's fallacy of misplaced concreteness. But more on that later. More recently, hyperspectral scans have been developed that similarly utilize projected light into the ocean, but to measure light wavelengths outside those of human visual capabilities. These scans produce numerical data outputs and representational images that squeeze these hyperspectral light wave spectrums back into the colors of the visual spectrum, kind of oddly, and can be used to measure the health of ocean ecosystems based on colorations we can't see in species like coral or seagrass. An example of the output is shown here. The technology is still in testing, and scientists find it difficult to take a consistent and even panoramic scan from equipment attached to a rigid ROV body that is floating around the currents of a fluid volume. As you can see in this recording, current technology best resembles a toy boat struggling on the open ocean. There we go. Another optical scanning method often used is laser diffraction. This involves measuring diffracted angles of light wavelengths, if you can believe it, sent from satellites to determine the size of particles in the ocean, from which distributions of biomass in an ecosystem can be extrapolated. And all these types of scans are not supposed to capture a comprehensive story of the ecosystem, but collect a narrow set of data from which broader conclusions can be inferred. Still, as you can see in the resultant images of these various optical scanners, especially in the bottom right of this image here, the outputs usually just resemble landscape maps, anything you all could do in this classroom. These abstracted representations of nature can provide broader insights on broader ecological relationships, but still represent a surface-based logic of projecting information on a surface, and use surface-based methods of light to measure and sense an inherently non-surface system. Like optical scans, sonar systems also require projecting stimuli into an environment to detect and measure what is reflected back by objects. But instead of using light, sonar systems sense differential pressures in the water. The deep ocean application uses an echolocation-like form of artificial sensing that is frankly no different from what you find on any fishing boat on any American lake. The resultant backscattering in the water delineates soft and hard to determine locations and makeup of objects, and when attached to ROVs, researchers can model the seafloor's topography, even differentiating between geologic components just below the soft silt at the bottom of the ocean, which you can imagine is of particular value to the oil industry. Sonar studies of deep ocean corals at NTNU by Garrett Johnson's team resulted in surprisingly detailed 3D models of the texture of the colony. I mean, not dissimilar to a landscape model found in a modeling program like Rhino or Maya. This sonar image, for instance, roughly looks like one of those models, which it frankly more or less is. However, all of these forms still rely primarily about surfaces. They're about finding objects in the ocean. Sonar is also used to detect and measure large organism populations midwater, giving biologists a rough sense of species population based on the frequencies of sound returned. The acoustic signals, which are projected widely into the water volume, though, are definitely perceived by other organisms because of the sensing organs like cilia and neuromasts that we discussed earlier. And these organisms usually respond to the acoustic signals and flee. Essentially, these types of scans require broad intervention into the environment that make the presence of the observer immediately known. In a kind of similar case, Garrett Johnson at NTNU's Department of Biology and the University of Svalbard found that in the polar night, where there is no light for months, right, in the Arctic and Antarctic regions during the winter, plankton fled the artificial light of research vessels as they would the moon or sunlight during non-polar night times to avoid predators. This speaks to the survival strategies of plankton that they evolved for their conditions, but creates a problem for measurement. Scientific knowledge of the deep ocean struggles with the experimental biases born from these types of constant challenges of the remote observation of an environment that natively contains different stimuli than our bodies can comprehend. There is not enough financial support for the sort of consistent long-term observation in the deep ocean that would need to make sense when you're only using a camera. This, for instance, is considered one of the better versions of consistent measurement in the deep ocean, which is just, or not in the deep ocean, but the ocean generally, and it's just a buoy with a satellite connection. It's kind of it. On a more absurd level, this ROV on the right of this otherwise messy table was bragged about to me as the best innovation at NTNU's AUR lab, which is in charge of all remote sensing research at NTNU and is one of the world's leaders in autonomous ocean research. Designed by a visiting Australian researcher, this is a cheap robot that is merely a camera and a propulsion system, and that's it. And the propulsion system can't even navigate in X or Y directions, but has propellers that propel the robot merely up and down the water column. The key, though, is that this robot can be built and deployed and then operated and maintained at a bargain basement low cost. It's the ease of use and inexpensiveness that makes this of such an innovation and is the height of technology in the ocean presently. So even the leaders in remote sensing are greatly constrained by cost, and the best technologies are not those best for sensing and modeling the environment, but are the ones easiest to deploy on a budget. This severely limits the type of questions that researchers can ask and the way they solve them. The scientific method requires a rationalized, revisitable area of study for experimental duplication that is only possible with consistent coordinates and elevations of observation. But unfortunately, the fluidity, remoteness, and groundlessness of the deep ocean makes that kind of rationalization difficult. In the midwater, there is simply no surface onto which you can project a Cartesian grid. NTNU's AUR lab is a pioneer of using GPS data to try to map a grid on an idealized smooth ocean surface. But as we saw earlier, ocean currents knock even the best prepared ROV off course, and GPS signals are not capable of directly communicating with ROVs through thousands of meters of water. Wires are still required. The two images currently on screen show a shallow water test setup for autonomous navigation using GPS. The GPS satellite connection is shown on the right, just plopped in the snow. And the images on the left show a computer with the ROV's route pre-programmed and the actual pathways that it's taken. The controls of which, for this very expensive equipment, are being administered from the passenger side of a car parked on the side of the road. Chapter 3. In the Philosophical Investigations, Ludwig Wittgenstein writes, "If a lion could talk, we could not understand him." Well, any lion tamer can tell you this isn't exactly true, as the tamer and the lion communicate through movement and kind of this delicate dance. We can also sort of imagine the extent to which it is true. The lion's vision, hearing, and sense of touch are constructed differently to humans, attuned to bands of experience that fit into their evolutionary niche instead of ours. There are feelings and sensorial reactions of the lion that humans simply cannot understand, and vice versa. Johann von Uexküll describes the species-specific sensory model of the world as Umwelt. Umwelt defines the cognitive model of the world that is formed by sensing and is molded by evolution in a species to adapt spatially to the world it navigates. The sensory world constructed by humans is not the sensory world constructed by a fly, which you can sort of see roughly in this diagram here, and that difference corresponds both to the scale of and environments within which each species operates, but also to the evolutionary niche each occupies. Just as a thought experiment here, imagine a tick waiting on a blade of grass, whose entire sensory world, entire sensed existence, is the detection of a single chemical. But from this one olfactory stimulus, the tick knows to jump, and when it does, it will land on a mammal, to burrow into its host to spend the rest of its life. To understand the world that is felt by another species, one must step outside our own species-based spatial biases and needs, which is a radical challenge for humans trying to understand and comprehend a deep ocean environment that lacks its body's tools for conceiving of space. Merely adapting mechanisms invented for the sky or shallower waters solves the wrong problem. ROV design, like building design, utilizes the architectural tools of orthogonal, perspective, and axonometric drawings that trace their origins to the Renaissance. In this sense, the problems of deep ocean rovers' Umwelt are one of architecture, as these tools have relationships baked into them that prioritizes the human construction of space over other entities. As architectural theorist Catherine Ingram describes in Architecture Animal Human, the asymmetric condition, Brunelleschi's invention of single-point perspective was reliant on an apparatus that constructed space from the focal point of a biped, and you can see that biped using that instrument here. The perspectival grid and transubstantiation of three-dimensional space into two dimensions form the foundation of architecture as a discipline and as a profession. Yet its logic is a construction, an invention to be used by humans, not an accurate description of how space physically works in the world. Brunelleschi's invention of perspective is from the perspective of the human, a tool for humans, and, as Ingram claims, emerges from a period intent on creating a barrier between the human and the rest of culture. The tools of drawing that are the foundation of our discipline put the human at the center of its world model. The drawing tools of architecture have evolved since, but are still finely situated for the Umwelt of humans, not other species, and especially not a robot. Our conception of architectural systems are by, for, and through the human. As a sort of thought experiment to attempt to break with and undo some of these biases and develop an architectural language that might speak to the other than human Umwelt, I collaborated as exhibition designer with artist Mari Bostashevsky for her show Pending Xenophora, which engages with her Unworld project. Pending Xenophora is a multi-layered world designed together with a route of garden snails, Yes, this is one of my favorite peculiarities of the English language. A group of garden snails is called a rout. But beyond that, they're working with a rout of garden snails and an aspirational gesture towards an idea of knowledge evolving, dependent on shared agreements and perpetual renegotiations between humans, animals, and technology. I am not the best messenger to describe Mari Bastashevsky's project. I mean, she is. But in short, and you can find videos on YouTube, I think, of her lectures explaining the project. But in short, Pending Xenophora is the result of several months working with a rout of snails, who are named the Unworld Collective, along with artists and programmers to design a augmented reality, or AR, experience for snails. This video game of sorts was intended as a form of interspecies collaboration in pursuit of digital pleasure. From that game, which the snails played on an iPad with lights and lines, Bastashevsky documented the behavior and interaction of the snails playing the game, and then translated the research narrative and data collected from the game into a VR experience for people. I designed the housing for that VR experience. The exhibition designed for Pending Xenophora desired to discover a snail architecture by translating the knowledge snails attain through movement into a virtual experience for humans, all while adhering to the cocoon-like aesthetic cultivated by the artist. I chose inflatables to try to affect the human audience's movement. As you can see here, a soft, slightly inflated floor acted as an unstable ground, forcing the VR audience to transverse the experience by crawling, a virtual movement for the virtual sight. Snails like traversing and hanging from every surface, so it was important that the architecture was in some way non-orientable. Though interestingly no audience member chose to try it, one could sit both on the exterior and in the interior of the membranes. The soft volume produced by the inflatables also adds aesthetically to the exhibition by acting as a surface onto which to project other snail footage from the research, while also slightly distorting those images, and just generally providing a gentle setting to enjoy the VR. A snail-inspired scent was also added to the air intake by a scent artist, which provided another sensory layer of virtual experience and immersion. In addition to design, I fabricated this housing. The work was shown this summer at the Digital Ecologies Conference in July in Bonn, Germany, and was later shown at Mediamatic in Amsterdam in late August to early September. This was a fun thought experiment, and I think was successful in some of its goals. However, human behavior was altered, but still not decentered. I think in this sense, the work was more effective as a layer of a virtual environment than it was as a non-human architecture. To return to the deep ocean, where it took technology and architecture to mediate a meeting between the human and snail on roughly equal terms, an ROV that is designed using axonometric diagrams with a surface-based understanding of structure and designed to capture visual footage will inherently have biases towards the spatial towards the spatial conditions of Earth's surface that is familiar to humans. The resultant spatial understanding will inherently be ill-equipped to understand the deep ocean as a complete ecology on the deep ocean's own terms. ROVs designed in this way will inherently be unable to communicate the inhuman spatial phenomena of the deep ocean because they are designed to only utilize human spatial mediums and spatial languages. In this sense, the mechanisms scientists use to sense the deep ocean for data collection are downstream of the spatial logics built into these superstructures. 3D modeling softwares like Rhino and Maya might seem to break from this world model enough that's implied by single point perspective in a way similar to the way space functions in the deep ocean. Digital objects, like deep ocean objects, appear to exist on the screen in an open space, free of ground, with indeterminate light, and might seem like a better design tool for the deep ocean than the orthographic drawings and representations. However, there is still a harsh divide between NURB and mesh objects and the infinite void of model space they occupy. 3D models are exported as tangles of mathematical equations that are processed and then only represented on a screen as an object. Its surrounding space has no relationship to the visualized object except as relief. This is not dissimilar to the sky in a perspective drawing, conceived as the relief for the foreground, a mere absence. While an object in model space has the ability to exist in multiple perspectives and be groundless like objects in the deep ocean, the infinite plane of the digital model is still a mathematical absence, just an empty graph. The oceans traditionally have been treated similarly, as the mere liquid void of a map instead of positive space. The Spillhouse projection, which you see here, maps Earth only by its oceans and is a rough attempt to sort of undo this assumption. But beyond the biomass housed in the deep ocean and the vectors of stimuli that reverberate through its volume, the deep ocean, like the sky, is filled with a fluid of chemical matter into which marine snow, salt, life, and other matter is dissolved. Objecthood is much fuzzier in the deep ocean than in digital space. Consider this a sort of inverse of Whitehead's fallacy of misplaced concreteness, a fallacy of misplaced void. Sloterdijk declares, "Tell me what you are immersed within, and I will tell you what you are." Objects in the deep ocean are not a presence among the absence of water, but an intersection where the messiness of matter is a mixture of water, mineral, and life, inseparable and even indistinguishable from each other, all interwoven together in a fabric whole called ocean, or as you might call it, hypersea. Where the virtual space of a 3D model is immersed within the absence of a graph, the space of the ocean is immersed within the dynamics of water. Chapter 4. Computers best meet the deep ocean not in the virtual simulations of 3D design programs, but in physical projects like Microsoft's Project Natick. This Microsoft initiative placed a bank of data center servers into the ocean off the coast of the Orkney Islands in Scotland. Data centers are the buildings or kind of centers that house the servers, computers, and infrastructure where the cloud, like Amazon Web Services, is physically stored. Project Natick, however, used the ocean's natural lower temperatures to cool the servers via submarine plumbing systems that do not require the energy usage of air conditioning. Computers clearly have different spatial needs than humans, and the Umwelt of computers are much better suited to the deep ocean spatial offerings than the human body. Data centers are a strange marriage where the infrastructure designed for the biological spatial comfort of humans is deployed for the comfort of machines, whose silicon and metal bodies regulate themselves outside the chemical need of protein chains. The results are excessive energy needs for air conditioning and server power when housed in a warehouse. These post-human ecologies of metal, which project to multiply with the expanded applications of artificial intelligence, are better suited for the darkness, slowness, and relative cold of deeper ocean conditions. There are already reports of China's desire to construct a data center military base somewhere at the bottom of the South China Sea, a kind of rough rendering of which is shown here. But before you panic and call the news, the technology to create and sustain such a base is years and seriously likely billions of dollars away from reality. So such plans are entirely premature, but merely allude to the deep ocean as a near-future home for computational infrastructure. These speculative near futures that place the bodies of artificial intelligence into the deep ocean exhibit an understanding of the robotic Umwelt better, I think, than the ROV advances of the last century. However, these schemes still see servers essentially drop to the bottom. The machine's relationship to the deep ocean at this point is one more of burial than active engagement. If ROVs are meant to make sense of ocean space for scientists, these drowned servers hold the possibility to experience space on its own terms, but they must actively engage with it. According to an embodied approach to cognition, sensory motor systems form cognitive models of the world through direct physical engagement. It is in contact, in closeness, where space, sensing, and the potential for awareness emerge. The world molds sensory motor systems through evolution to feel the world they are immersed within. A co-productive relationship where the mind of an organism is inseparable from its body's spatial interaction with the world. Every species is finely tuned, like an instrument, for the world it exists within through the movement of its body. It is movement where a body meets an environment. And in a fluid world like the deep ocean, architectural intervention for other than human entities must also flow sightless in the currents. It is subjecting architecture to movement, not fighting movement through structure, where a knowledge of the deep ocean that is of the deep ocean can possibly emerge. And, like Wittgenstein's lion, or the processes that form knowledge in artificial intelligence, we humans, we're never going to understand it. It is in this paradox that I, along with Lauren Kirk, developed a speculative project for the deep ocean called Data Center of the Sea. As mentioned earlier, data centers are a green disaster, consuming 416 terawatts of energy each year, and that energy usage is projected to double with every preceding year. The machine-centric buildings that house these servers are designed using infrastructure meant for human comfort, resulting in carbon-soaked buildings ill-suited for their other-than-human inhabitants. Why is architecture for machines designed like architecture for people? If humanity hopes to avoid catastrophic climate change driven by our use of machines, architectural systems should adapt. The Data Center of the Sea hopes to evolve machines to suit environments on Earth that are inhospitable to humans currently. Where humans need light, comfortable air, and a stable ground, as we've discussed, machines are better adapted for the fluidity, cold, pressure, and volumetric groundlessness of the deep ocean, of the ocean in general. These linear, mid-ocean data centers run along thousands of miles of sub-ocean communication and internet cables, establishing a sustainable relationship between machine and world, lines of a single module networked on a global scale. Like Microsoft's Project Natick, this project takes advantage of ocean temperatures to cool servers without energy-sucking air conditioning. But instead of structural systems designed to maintain a constant ground, this project is structured to bloom in place mid-water with Buckminster Fuller's jitterbug geometry. And here you can see like a rough schematic where we have a server module, a battery module, and a hinge that generates power in its movement, which we'll see in the next slide. The jitterbug, formerly called vector equilibrium by Buckminster Fuller, starts with a cubooctahedron, and this transformation you can see on the right, which collapses in on itself through icosahedral, octahedral, and tetrahedral stages, and then is inside out again. It's this blooming process. Data Center of the Sea activates the jitterbug transformation with water flows, turning the massive but slow kinetic energy of marine currents into carbon-free energy for machines through the movement of its structural members, like a windmill for the sea. Servers and batteries fill in the stable surfaces between the more rigid structural members and are tethered to transocean internet cables, which allow it to jack right into the internet, following along the transocean internet cables diagrammed here on a spillhouse projection of the Earth. In this conception, units are connected in strings, as you can see here in this water column section, forming a pulsating machine landscape suspended in the ocean. This project was shown in my previously mentioned solo show in Trondheim this summer, and later shown in Berlin this autumn as a part of Tactical Tech and Hibel M. Ufa's exhibition Everything Will Be Fine during Berlin Art Week. It was housed as a board within this structure, and unfortunately, despite a few attempts, we didn't get great images of the work in the installation, but here are two very clearly high-quality screenshots that I took from Tactical Tech's Instagram. This is what the panel of our section that you saw poorly in the last two slides looked like in sort of a straight-on view. Artworks and projects that explored issues or sought solutions to a series of overlapping global crises were shown in the show and discussed along several topics. Data Center of the Sea was highlighted in the Digital Doubt section on the Rethink board. Inspired by this work, I began searching for models for an other-than-human architecture that could be in tune with the midwater deep ocean's fluidity, groundlessness, and motion. I began various spatial and structural experiments late in the Fulbright, but returned back to working with Buckminster Fuller's Jitterbug based on the earlier iterations of Data Center on the Sea, and just found it most compelling of the different options I explored. I want to reiterate that this part of my research is rough and still incomplete. Only the very initial stages were explored in Trondheim. But they did reveal the challenges I want to formally address in the next phase of this research, whenever I finally get appropriate funding and venue. While designing structures and animations in the computer is complicated in its own way, it turns out making physical, functional jitterbug units provide a different degree of challenge. In conjunction with my show, I hosted a workshop at NTNU for architecture and art students that culminated in the construction of smaller jitterbug units by the students in the workshop. The act of making a geometry with your hands lends a certain tactile knowledge to the dynamic. As my own students in my studio, I think, have figured out, students struggled, but with help not only built their own versions of the jitterbug, but gained an advanced understanding, one I think both conceptual and tactile, of the geometry structure. The hinge design in the jitterbug must balance precision of movement with construction tolerance for my fat fingers, and various imbalances at different phases of assembly. Admittedly, I still struggle to find the right balance, and have broken more models in these early iterative phases of research than you can possibly imagine. In Trondheim, I dealt with probably around 8 different types of glues, drawing from craft, hardware, and marine applications, to hold the triangles together and smoothly moving. I collaged joints with 3D printed parts. This was much easier at smaller scales, but became quite problematic at larger ones. The latest stage of these very early iterative experiments were these units with 1-meter-long members built out of carbon fiber that were eventually exhibited as part of my solo show in Trondheim. These works were displayed with a unit in its closed state next to a recording of the artist activating the geometric transformation. Even though the triangles best resemble our assumptions of what structure is in architecture, the structure of the jitterbug is found in the joint. Fuller himself struggled to make self-sufficient and structurally stable jitterbugs because the geometry structure lies in this Dreyer hinge, which controls the two-planar rotation between triangles. It is motion that defines the jitterbug, not static stability. In worlds without stable ground and flowing viscous fluids like the deep ocean, it is the fluidity and groundlessness that are the base attributes of its space. Should not architecture adjust in its structural challenges? The physical nature of the model becomes a diagram of sorts, for an architectural gesture towards movement. An abstraction that articulates the dynamic possibilities of this transforming geometry unbound from specific site and exact architectural application. The ambition of these explorations is to figure out the geometric and engineering factors that matter in the design of transformative geometry for an architectural context. As humans continue to affect Earth's atmosphere and begin to explore extraplanetary environments like Enceladus, our relationship with other-than-human entities will force us to shift towards a post-humanism that, while currently getting explored on the edges of our discipline, has been limited to applying human-oriented structures to other-than-human users, or translating other-than-human bodies into sorts of symbolic uses for human-based structures. These jitterbug experiments, ones already performed and to be performed in the future iterations of this project, and hopefully many more of those, are the beginning of my attempt to break our own species and disciplinary boundaries in hopes of establishing a future where our relationship to the rest of the world can be productive. The big takeaway from my research is that the deep ocean is inherently not for us. And any architectural intervention or engagement with the deep ocean will have to cede primacy to the other than human. Thank you. That was really fun. Great.
So I know that this question sort of came when you were showing the data centers in the ocean, the floating ones connected to the internet cables.
Mm-hmm.
So I question how you balance, especially, I mean, your studio, you know, we're doing data centers. I know we're working on doing architecture for the computational body in addition to the human body and how the sort of computational body experiences space. I wonder how you balance the known versus unknown elements of designing something like a data center. And, you know, if a data center is in that closet, we know the stimuli that's going to influence it.
Mm-hmm.
If something in the ocean, you never know if a whale is going to run into it. You know, you
Yeah.
don't.
No.
So, like, how do you sort of find that balance between the control that is possessed by, I think, conventional Cartesian architecture,
Yeah.
and the unfathomable unknown of designing for other than humans?
No, that's a great question. And so there are some very, like, roughly simple answers to this. And so it is amazing the amount of sensory inputs that we as humans understand exist, but can't feel and comprehend. And in this case, there is a strong electromagnetic sense as well. I talked mostly about cilia and neuromass because this is quite typical for deep ocean life, but there are also a strong sense of, like I said, an electromagnetic sense that actually it turns out humans have a little bit as well. There are a series of really fascinating and wild studies from the 70s that showed that they would put, they basically, like, you know, in movies when they throw someone into a van, put a bag on their head, and like drive off. So a series of psychological researchers did this, and then some people though had magnets like around their head, and some people didn't. And it was actually statistically significant that the people without magnets were able to get back faster than the people with magnets. It wasn't much, and it's debatable, but it is a technically significant, statistically significant amount, which is just a really bizarre, funny study. It also turns out cottons, our electromagnetic sense handles cottons better than synthetics, and it's really best to be naked. But not saying to test that out in Hutchinson Hall later this afternoon, but as means to say that, right, there are different forms of sensing that can happen that are still outside of our basic and normal comprehension, and that deep ocean life has. This is a big issue, again, with experimental biases, where the observer is almost immediately known. And to attract forms of deep ocean life, especially in the deep ocean, oftentimes researchers have to entice life with other attractors to kind of bring them in. Again, one example was of Edith Witter, who's a deep ocean researcher, she was the one who eventually found the first photographic evidence of the giant squid. Had to use a basically machine that mimicked a jelly, like a jellyfish, to actually eventually draw the giant squid. There are other tricks that a researcher has to do to really observe these deep ocean fish and life up close. So a data sorter would inherently have some other sensorial aspects that, while we might not be able to comprehend, deep ocean life could. Similarly, data centers often break down, right? Data is usually stored in multiple places, and oftentimes shorts, breaks down, and it's the duplication of information that kind of saves that information. And so there is this understanding that if it was in the deep ocean, perhaps, or in the ocean at all, flowing more freely, that that information would be duplicated and could be rearranged and would potentially not have any more incidents or accidents as a normal data center might, what we think of as a normal data center might have. Yes.
I'm just curious, in your work, how much do you contend with the ethics of design and building an ocean? Right? To me, it seems that we already pollute the
Yeah,
ocean a lot.
absolutely.
Okay? Is this a consideration that takes into account? Like, we already have the surface, right? There's enough of it. We're not using
Yeah.
all of it already, and we already know ways to build smarter, basic, right? Building up as opposed to out. Like, would this not be another example of kind of like building out?
Certainly. So, admittedly, some of the other work that has been involved I didn't show is I was working with, I've worked with some colleagues of mine who do a lot on deep ocean mineral extraction. Interpret Nabil Ahmed at NTNU does some really exceptional work, and his film Blue Peril is very much worth watching if you can. And right now, deep sea mining is a huge topic, which is fascinating because it's an entirely speculative industry. It turns out that there's not really the engineering or technology to do it at a mass scale, but they have to keep scamming investors more or less by getting licenses and like showing progression to keep up that logic. In terms of extending the human into the ocean, right, and expanding the project. So just to say that the environmental aspects of the ocean is something that I am concerned with generally. Now, specifically into the extension of human influence to the ocean, I think the point of a lot of my research is that, or of some of the work, is twofold. I think one is this acknowledgement actually is that the deep ocean isn't for us, right? And that when we think of architecture, we have this automatic assumption that it's for human use. And the idea, I think, before a lot of this insertion of artificial intelligence or computational systems into the ocean is more about finding what's right for computation. Treating the robot, treating the computer as an entity that might have its own life in a way that we fundamentally can't comprehend. And what is best for the computer as opposed to best for us. And I think in that sense, the deep ocean might be a better place for artificial intelligence. It might be a better place for these forms of entities to craft their own understandings of reality.
Towards the end of the lecture, and kind of like the similarities with the atmospheric questions. So the opposite of that, like space might be a better place, right? There's not like fish and nice whales and disturbed out in space.
Hey,
So it's like,
space is the place, right?
but I understand it's more expensive to get something up there and off the data center, but so you can only be focused on the kind of like the economic aspect.
Well, I think this is one of the ways that I think this deep ocean research is valuable, right? Because space, like the deep ocean, is a space that deprives humans of our ability to both survive and understand. And I think that what the deep ocean allows is a sort of test case, a sample, onto which we can start to think about these different forms of spatial understanding, because there are living things in it. It is closer than space, certainly, even though explored much less. And it's the sort of tools and techniques that we can begin to understand about the deep ocean can be applied to other forms of what we might call other than human spaces or other than human environments. So I think certainly, and I'm not here to say that to advocate necessarily for let's start investing all of our money for Google to put a bunch of robots into the deep ocean. But I think there are lessons that can be learned, because the deep ocean, again, is this somewhat familiar yet somehow incredibly foreign environment that I think provides an interesting test case for these forms of thinking.
I think we probably have time for one more question.
The dean gets that privilege.
First, congratulations on a really well-written and well-presented and well-illustrated lecture. Very articulated and very well done, so that's terrific. This morning I took my dog Gus for a walk, and we go out and he gets to sniff everything you can imagine. And it's always a moment for me to remember that what I'm looking at, he's understanding not just through what he sees, but what he smells.
Mhm.
And what he smells is time. He understands who was there when, right? In a way I can't begin to understand it all. But for him, it's a description of another sense. And I'm always reminded of how little I know compared to him
Yeah.
on those walks, which is great. And I see that in, I think, this really almost noble effort on your part to begin to assess an environment and understand how we can engage with it, what places we have ultimately, where the limitations are, and how we make our own accommodations to that, which is great. And the work is fascinating. The inventiveness, where you're taking it all is great. I want to ask you though,
Yeah.
does it at any point bring you back to this world and understanding the environment of this world in a way that goes beyond what we're used to, whether it's our own education through Brunelleschi's idea perspective? You know, there's some people who say look back to the Japanese drawings from the 6th century, which are done without perspective,
Yeah.
but are far more accomplished in many ways in terms of depicting the world than what we expect from the Renaissance.
Yeah.
And it seems to
Great
me
reference.
you're sort of, you posited such an enormous question to look more deeply at what's around us in a way that we can engage with as architects.
Mhm.
And where are you in that quest?
That's a great question. So I think for me it comes back to a few points, and that, right, as I mentioned in terms of the earlier question, is that, you know, the deep ocean is a chance to sort of escape our pre-assumptions about how space operates, because it doesn't operate against those same rules. And I think this is part of the understanding, is that, you know, the deep ocean isn't for us. And so when we start thinking about it, it then makes different implications. I think there is an exercise in empathy that is very difficult, that is inherently implied when you start thinking within our disciplinary toolkit how to evolve it and change it for these sorts of non-human spaces, that can be easily applied back to the surface level. I think, as I briefly discussed in the lecture, is that we are engaged in post-human thought. It is something substantial both in philosophical and architectural contexts. You know, Donna Haraway is readily common reading in graduate schools. And yet in architecture, we seem to find that these uses for thinking about the other than human, thinking about a post-humanism, really are either, hey, we know how to build stuff, let's just build it for a penguin, in the case of the London Zoo. Or coming from Pratt, we were, where I did my MArch, we were very much involved in a look at an animal, see what its body can do, and integrate that into some sort of architectural use. And I think this is not taking the other than human seriously enough. And I think you start to see it most in this exhibition design that I did for Mari Bastashevsky. And that the point is that what we can bring into our surface is an advanced and maybe increasing attempt to really understand the other than human in architecture. Our discipline fundamentally puts the person first. And so I sort of started to see some of that in terms of we coming out mostly in movement, and how we create structures and surfaces that affect how we as humans might move, or create structures and surfaces that are really more applicable to the movement of other than humans. The original, way back when I first set out on this assignment and got this funding, my idea is what I really wanted to do was to find an installation that somehow translates deep ocean space for humans. And that was the real challenge. And after working and doing some data collection, I came to the realization that that just wasn't possible, right? Again, we don't have the sensory apparatus to make sense of any of these things. So what can we do is think more seriously about the other than human. And I think that's the real lesson to bring in, is that there are things outside of our understanding, Yet as architects, we are designing in a world that exists that is occupied by different species, different organisms, and not just people. And what does that mean then? That is a sort of responsibility. I mean, even in the AIA's own commandments or policies, is that it is a humanism is put forward. You're designing for the client. But we're also designing for a world that is out, and many of those functions and entities don't have money to hire architects. Yet that should be a part of our responsibility. And working on those abstract empathy tools, I think, are important and also can be developed as more tangible applications later on. I mean, in terms of what's being used in architecture, bird-safe glass, I think, is an excellent start, but probably not far enough. In thinking about, for instance, how birds might occupy and interact with architecture. And so this comes in a series of small studies. I'm admittedly, as someone who borders a little bit of architecture, a little bit of art, more interested in maybe these more far-fetched forms and structures. But I think there is a practical application that does work its way into my work, and for those of you who've taken my studios into my studios, that maybe is best to be continued to explored by other people, and I encourage everyone to sort of start thinking about these things in these ways.
Thank you so much.
Thank you.
I don't know.
Yeah, no worries.